Hello everyone. Can you guys hear me? Hello. Okay. So let's wait for 5 minutes to everyone to join and then we'll start today's live session on modern construction material undertaken by Professor Ravindra Gettu from IIT Madras. I am PMRFTA for this course. My name is Umesh Shule. Let's wait for some time and then we will start today's live session. Okay. I hope you guys have already attended all the online lectures and you are well prepared for today's live session where we will study overview on week 3 because already week 1 and week 2 assignments we have already covered, and in that we have seen a different type of atomic configuration, the type of bonding and Condon-Muns diagram, and different type of bonding, how they changes the property of the material and the selection of material, and many other topics have covered in first two uh, live session of this course. And in this today's live session we will be covering atomic bonding, in which specifically we are focusing on the movements of atoms, how the atoms move into the material at the very nanoscale, how these atomic movements are influenced in the different materials, and what these atomic movements lead to change in the properties of material. Also, we will study the small and large type of movements, like what will happen if there is a small movement and large movement. Let's, for example, if the movement is smaller, uh, okay, people are joining now. Okay, okay, I'm not able to continuously add you guys, so please be online. Okay, so we were discussing about that we will study the small and large movement of displacement into the atomic structures. Like, for example, the small amount of movement can lead to a change in the shape of material, but it can regain its original shape, like it can be under elastic limit. Time that type of movement we can call as a small movement. However, when there is a plastic deformation happening into the material, we can say that the large movement is happening in between the atomic particles. And how these movements, small and large defect movements, are influenced by defects, we will study, and how these defects provides the path for this movement we will study in detail. Also, like the defects lead to formation of slip, dislocation and diffusion type of movement. We will study in detail what are those and how material changes its property according to these three different behaviors. And finally, we will also study some of the basics of phase diagram. Okay, so let me start with the overview about the movement of atoms in lattice. As you can see it here, the interatomic forces and distance. The first lecture we have studied the Condon-Muns diagram that simply state about the energy versus distance diagram. You can see it here. When we differentiate it with the distance, again with the energy, we can get a force. Okay, after differentiation of this curve, we will get curve like this, as you can see it here. And you can see when the distance is very less, the repulsive forces may be even predominantly higher than the attractive forces, because the same type of atoms will come together and they will try to repulse each other. Okay, and when there is a equilibrium distance at that point, there is a minimum force required for to hold them together. However, when the distance is again increases, the attraction forces in that material starts. So we can say that this is somewhat analogous to stress strain curve of any material. And here is the one of the example. You can see that the larger is the slope, stronger is the bonding between this material, and we require a very high amount of force to take away uh, increase the distance between two particles, and this can be seen as a example of weak bonding. Okay, so this is the force diagram, and we will see like how to use this in solving some of the questions. Okay, so next we will be studying the what is slip along the atomic planes. So what is slip? So the plastic deformation that remains after the load is removed of the metal occurred due to the slip along the atomic planes. Okay, so the plastic deformation happens to the material which can't regain its original shape of the metal occur due to the slip along the atomic planes. Okay, the slip happens along the atomic planes. Let's see how this happens. The extent of slip will depend upon some of the characteristics of slips are the magnitude and direction of shear stress. More the magnitude, more the shear stress, and that will lead to more slip. Bonding between atomic planes. If the bonding is very strong, we require high amount of stresses to create a slip. Okay. So in a crystal, slip occurs along the plane on which the atoms are almost closely packed. Okay, remember this. In a crystal, slip occurs along the planes on which the atoms are mostly closely packed. Okay, people are joining a little late. That's no problem. Let's move forward. Can you guys see my screen? Just raise your hand, or maybe just uh, say yes. Can you guys see my screen? Or maybe just raise your hand, no problem. Or maybe just text in a chat box. Now you can't see, but now you can see. I can't see both the screen today because I have limited screens today, so please bear with me. Just send anything like you can see or not. I think you guys can see. Okay, so let's take the next question. So regarding the sleep, just we now studied what is the sleep, and there is the first question. Which one of the following statement about the sleep in a crystal structure is correct? Right? So like just now we study the sleep. So sleep occurs when the dislocation moves along the specific crystalline planes under applied stresses is the first answer. The second is sleep can occur in a random direction within the crystal. Maybe true. Sleep results in a formation of new grains with the crystal. We don't know. Let's see. The final option is like sleep is not influenced by crystal structures of material. So which one of this is correct? You have to answer. I appreciate if you guys unmute yourself and say the answer, because that will prevent me to swipe the screen and look at your answer on chat box, because I don't know, I can't open chat box right now with the same screen. So please answer. We'll wait for 2 minutes to everyone to see like what is the sleep and how the sleep will occur and what is the characteristics of sleep in a crystalline structure of material, how sleep occurs. Okay, so let's see the answer. And the answer is A is correct. Yeah. Sleep occurs when the dislocation move along the specific crystalline plane under applied stress, as already I have explained in the previous slide that the yeah, I already explained in the previous slide that the plastic deformation, the crystalline in a crystal, sleep occurs along the plane on which the atoms are most closely packed. Okay. So yeah, answer is correct. And here is the example of sleep. You can see it here. The first position of these atoms were here. Okay. And now they have moved to this location. Okay. So everything is shifted towards right. So this is called as a sleep plane. Okay. Which happens at the atomic level into the materials. However, there is a different type of movement is also possible in some of the materials, like which is called as twinning. So what is twinning? In that the sleep doesn't occur, but uh, the whole like atoms are shifted towards the new position from the previous position. Let's say this was the previous position, now the new position happens, everything is shifted. So just to perspective in this regards, like which one of this will require high amount of energy to occur, sleep or twinning in a material? It's easy, just see the amount of displacement required by atom is where is it is more. So more the displacement is required, more amount of particle has to be shifted from one place to another. We require high amount of energy. So which one will have required the highest amount of energy? Sleep plane or twinning plane? It's easy, like the answer will be twinning plane, because we require large amount of forces, large amount of energy to displace a lot number of atoms compared to sleep. So twinning require a high amount of energy. So the next question is that which one of the following correctly differentiates sleep and twinning in crystal structure? Just now we studied the sleep and crystal structures. Try to answer this. It is easy. The sleep and twinning both involve the motion of dislocation in the same manner. Twinning is dominant deformation mechanism in ductile metal, while sleep occurs in brittle material. May be true. Sleep and twinning always occur simultaneously in all the crystalline materials. We don't know. Sleep occurs along the specific crystalline plane, while the twinning results in a symmetrical reorientation of crystal lattice. Yeah, just we have seen example of sleep and twinning. It will be easy to answer this. Please try to answer, and then we'll move forward to the next question. The question is easy, like what is the difference between sleep and twinning in a crystal structure? Just we have now seen differences between sleep and twinning. Twinning required a more amount of energy, just we have studied sleep required a less compared to twinning. And the answer of this question, let's see, is answer D. The sleep occurs along the specific crystalline planes, while twinning results in a symmetrical reorientation of a crystal lattice. Someone just join, I guess. Okay. Okay, let's move forward to the next question. Yes, so the next question is regarding the dislocation. Which one of the following correctly describes the dislocation moment in a different type of materials? Right? The dislocation moment is easiest in metallic material due to the non-directional bonding. Just recall the week 1 live session where we have studied which type of bonding are directional, which type of bonding is non-directional. Now the question says that answer says that the dislocation moment is easier in metallic material due to non-directional bonding. Now just recall that is the metallic material have non-directional bonding. Covalent material exhibit high dislocation mobility due to strong directional bonding. Now, yeah, just for example, covalent bonding is directional bonding. Yes, true, but is it required high dislocation mobility? Exhibit high dislocation mobility? We don't know. Okay. Yeah. Third question. Third answer is ionic materials allows easy dislocation moment because of strong electrostatic attraction. Dislocation moment is easy. The last option is the dislocation moment is equally easy in metallic, covalent, and ionic material. Try to answer it like try to say which one will exhibit the highest amount of dislocation compared to ionic, covalent, and metallic. Yes, please try to answer this question. It's easy, like which one of the following correctly describes the dislocation moment in a different type of material. So the question is about you have ionic bonding, covalent bonding, metallic bonding. Which type of bonding will have highest amount of dislocations and why? The hint is given into the picture. Here you can see the covalent solid, some amount this directional bond is shown, and ionic solids a different type of charged particles are shown. This is the hint for the answer. Try to guess what is the answer. Everyone is joining late. Okay, no problem. Try to answer this. Take some time. If you do not understand what is the dislocation moment, then you can just unmute yourself and just ask. If you guys don't understand anything in this question, just ask, because maybe you have missed previous explanation of dislocations. Yeah. Anyone? Guess answer is also fine. You can just type in chat box, no problem. Okay, let's see the answer. Answer A is correct. The dislocation moment is easiest in metallic materials due to non-directional bonding. Of course, here you can see the example. Let's say if you want to dislocate this plane. However, due to the directional bonding of covalent bonding nature, we require high amount of energy to break these bonds, right? Hence, covalent bonds will require high amount of energy to create a dislocation. In ionic, motion itself is difficult because the neighboring charge is not same, is different. Let's say you try to make dislocation happen, but then this same type of charges can come together and they may repel each other. Because of that, whatever was we try to do may not be possible. So hence in ionic solids also the creation of dislocation is not that easy, and hence compared to metallic material where the directions is the bonding is non-directional. Okay. So dislocation moment, if you I want to explain you guys in detail. So the grain boundaries are the barriers to slip, as I think we have discussed this in the second lecture of live session series, where I have mentioned that the why grain boundaries occurs, because when there is a crystallization, the grain growth is happening. Okay. So this may be the nucleation point of this grain growth. This can start in all the direction possible. This will grow in the all direction possible. This will go in the all direction possible. However, when there is not enough space available, this nucleation part and this nucleation of grains will collide each other, and this collision may be parallel, may not be parallel. Okay. Mostly there is a possibility that they will not be in the same direction. So, they will be little bit discontinuity in their directions, and they may not be parallel. So, and the dissimilar materials may create in this location, and that is called as a grain boundary. Okay. So, this is a grain A, grain B, and between this is called as a grain boundary. So, what is our motive of studying this? When there is a slip plane is occurring in one of the grains which may travel along this grain, right? Just we have seen that what is the slip, right? Or maybe tuning can also happen here. But when they come at the location where there is a grain boundaries, now the orientation of atoms are changed. Because of that, the slip propagation becomes difficult, right? So, because of this slip misorientation is there, right? Barrier, it acts like a barrier, and because of this misorientation, the slip may not continue further in this direction alone. So, it prevent the slip from occurring. So, that is good. Let us see. The smaller the grain size, more the barrier to slip. Okay. So, the smaller the grain size will happen, there will be large amount of grain boundaries and large amount of misorientation will be there, and if there is a possibility of formation of slip, the grain boundaries can prevent that slip from occurring, and yeah. So, the material may behave very stiff and may not behave in a ductile manner. And the reverse is also true, that if the grains are very large in a size, let us say the grains are little bit larger in size, then this characteristics of pure metallic pure material characteristics come to the play, where where the slip can easily occur because of the less number of grain boundaries are there, and such material may be more ductile, and but strength may be reduced. Okay. Yeah. So, let us see about what is next topic is about atomic diffusion. Just now we have seen the slip dislocations, now just see the atomic diffusion. So, what is atomic diffusion? When two different type of materials are coming together, and when we heat them at a particular temperature, or when we provide some amount of energy to them, they will diffuse from each one to another, and the center part will have alloy formation, where there will be the composition of let us say material A and material B, both will be present, and that is called as atomic diffusion. So, many reaction and processes really rely on transfer of mass, right. So, this is a type of mass transfer either within the specific solids or from liquid or from gas or another solid phase, right, anything is possible. Okay. This accomplished by diffusion, this phenomenon of material transport by atomic motion. So, diffusion happens because of there is a variation in the concentration. The concentration of B is very high here and concentration of A is very high here. So, as per the Fick's law, the concentration will flow from higher concentration to lower concentration. The same is applied for both the material and they will try to form an equilibrium. But for attaining that equilibrium, the materials required particular amount of energy, which is called as an activation energy, right? If that activation energy is not provided, this material may not stick to each other. Like for example, just say, uh, for example, let's say you have two stones in your hand and you are attaching them together just by your pressing by your hand. Will they become one stone? Obviously not, right? They will not become one stone. But for if you want to make this two stone a one stone, you have to give them particular amount of energy. So high amount of energy is required when they will convert their shapes and their states to liquid state, and then they can become one unified material. Okay, so yeah, the activation energy is required to start atomic diffusion. It is not that easy, and it is depend upon the material properties. Okay. Okay, so next question regarding the diffusion. Just now we studied what is the diffusion of atoms and which one of the following is correctly describes the atomic diffusion in materials. Okay, so the first answer is diffusion occurs faster in metal than ceramics due to the weaker atomic bonds. Diffusion in solids only occur through vacancy mechanism. Atomic diffusion is independent of temperature. Diffusion is slower in metal with the high concentration of defects. So just now we studied that regarding activation energy, we require some amount of energy to create diffusion. So, and a little bit background knowledge, try to answer this question. Just unmute yourself if you are want to answer, because now it's today. Sorry for that. I am not able to see the another screen of chat box. Okay, so let's see the answer and then we'll discuss one by one. So answer A is correct. The diffusion occurs faster in metal than ceramics because due to the weaker atomic bonds, right? Ceramics will have very strong bond attached together and they will not diffuse, and it will require very high amount of energy for ceramics to create a diffusion bonding. And diffusion of solid only occur through vacancy mechanism is not true, because there are other mechanism also, from that also the diffusion may occur. And atomic diffusion is independent of temperature? Absolutely not, as we have studied that the some amount of activation energy is always required to initiate the atomic diffusion. So it will be dependent upon temperature, right? And diffusion is slower in the metal with the high concentration of defects. This is not true, because uh, diffusion will be higher at the high concentration, right? The higher the concentration of defects, they will be unstable metal will be the unstable material that can be, and that's why by making the atomic diffusion bonding it may become stable. So that's why diffusion may be higher. Okay, so the next question is regarding the de-icing salt, NaCl, called as normal salt, which we use in cooking also. is an ideal suitable option for clearing roads in polar region during winter. True or false? Very easy. Polar region. So this be specific. Polar region means it's very negative temperature. Let's say minus less than minus 15 degree Celsius. So it's very negative. And can we use de-icing salts to melt down this ice? De-icing, right? It's like melting down the ice. Yeah, true or false? Okay, so answer 2 is coming. Let's see. Answer 2 answers are coming true. Okay, let's see. Yeah, specifically I have taken this question to clear some of the doubts. Anybody with a different answer? Okay, so yeah, anybody want to explain why it's true? Like, have you guys noticed it? Like, some of the people in the cold region are using salts to de-icing purposes. If anyone is from the Kashmir region with us, they can explain their experience. Okay, let's see the answer. Oh, so it's answer B is correct, not A. It's false. We can't use normal salt. So the answer for this is because it is not effective below minus 50 degrees Celsius. It's not effective. The polar region means that it's having very negative temperature more than minus 15 up to minus 30 degrees Celsius also, right? Because of that, when we use even salts, the NaCl salt is preferably not good to use because it's not effective. Its effectiveness is only good when the temperature is above minus 50 degrees Celsius, like 10, minus 10 up to 10 is fine, minus 10 is up to fine. Is that in its effectiveness is good. And there are different type of salts which can calcium based salts, chloride salts can be used, which is more preferable and less corrosive, right? Because NaCl is also problematic for infrastructure, like if we have a bridge and if the bridge is made up of steel, then the NaCl used for the de-icing may create a problem of chloride induced corrosion in this type of structures, where steel will start corroding very heavily and we will lose our structure. So yeah, that's why NaCl is not recommended. And other compounds which are less corrosive and less expensive than and less more effective in lower temperature is always recommended. Okay, nice learning. Let's move forward to the next question. Okay, which one of the following statement about the phase diagram of material is correct? Just now we have seen that what is the phase diagram, or maybe you have studied in the class like what is the phase diagram. So phase diagram shows the relationship between temperature, pressure and combination of phases in the material. A binary phase diagram, only single phase can exist at any given temperature of the and composition. The eutectic point in the phase diagram represent the highest melting temperature of the mixture, and phase diagram are always applicable to the metallic alloys and not for ceramics or polymers. These are the 4 options. We have to answer one by one. Okay, you can answer in the chat box also, that's no problem. Option number, phase diagram. Phase diagram represents the dash and dash and dash. Anyone with the answer? Okay. Till now, no answer. Okay. Okay, let's see the true or false type of. We can have 4 questions now. Uh, the phase diagram are only applicable to metallic alloys and not to the ceramics or polymers. True or false? It's easy, right? Now we will go one by one. True or false? For the D option. Can we have phase diagram for any material? It's like simple question. Or it is only applicable for metallic material, metallic alloys, and not for ceramics and polymers. True or false? Anyone with the answer? Okay, I will try to give a hint. The phase diagram is of course for every material. We can have phase diagram for all materials, so it's not only applicable for metallic alloys. It can be for ceramics and polymers too. Hence, D option is gone. Now A, B, C. Okay, let's see the answer and then we will discuss one by one. So answer A is correct. Yes, the phase diagram shows the relationship between temperature, pressure, and composition of phases in the material. Right. In binary phase diagram, only single phase can exist at any given temperature and composition. No, in binary phase diagram, two phases can also present. That's called, it is called as binary phase diagram, right? And the eutectic point in the phase diagram represents the highest melting point. Is not true. It's lowest melting point. Okay. Let's move forward. So this is the phase diagram. You can see it here. The phase diagram is a graphical representation of combination of temperature, pressure, and composition, or the other variable for which the specific phase exists at equilibrium. Right? The temperature on the x-axis, pressure on y-axis. When we play any material with the different type of temperature and pressure, we can convert them into different phases, right? Solid, liquid, gas. Okay, when the temperature increases, obviously everything becomes gas, right? For example, let's say you have ice here. Okay, ice made up of water, right? H2O. When we increase the temperature of ice, it will directly convert into the gas, sublimation, right? The gas can again converts into ice, which is called the deposition, right? True. Okay. When the gas is not converted into a solid for particular temperature, then we can take help of pressure, right? We can pressurize it to become a solid, right? So yes, you can convert things from one state to another by using temperature and pressure, right? For example, solid can become liquid when the temperature is increased. Obviously, the ice is melting, can be example of that. It's melting. Freezing is reverse, like liquid is becoming solid. It's like freezing of water to form ice is as also possible. Liquid becomes gas. Vaporization, right? Vaporization, right? Is possible. Vaporization of water, you can say that the temperature is increasing, the water liquid is converted to gas and evaporates. And when the temperature is slowing down, the condensation happens and you can see the droplets of condensation because of decrease in the temperature. Okay, so this is possible. Okay, so there is one triple point where everything is coexisted, solid, liquid, and gas in 3 state for the particular temperature and particular pressure is called as triple point. Okay. Okay, this was regarding the phase diagram. Then hence this proves that we can change the state of material by playing with the pressure and temperature, right? For example, let's say you want to carry a lot of CO2 from one place to another. You can pressurize it. When we pressurize it and when we reduce the temperature, that can be converted into solid, and then solid is easy to transport compared to gas, because gas requires a lot of high volume, solid doesn't require that much, and this is possible, right? The example is also LPG cylinders, where uh, in the high under pressure, the petroleum, liquid petroleum is under pressure, is put it inside. So due to the high pressure, it is under the liquid state, but when we come out, it becomes gas, right? Yeah, so if there is no pressure into the cylinder, then it will not be in that state, right? Okay, so the next question for the same uh, type of question is like, which of the following factor most significantly affect the solubility of material? Solubility is like, let's say you have sugar and you have put it into the water, now you are stirring it, now it's become solution, that's the solubility of sugar. So like if I want to dissolve a lot of sugar in my water, what I can do? Can I play with the temperature and pressure? Can I play with the size of material particles? Can I play shape of the material? Can I play color of the material? A, B, C, D. Try to answer. Just now we have seen that if you want to solubility to have higher, what is that characteristics of think we can deal with to enhance the solubility? Okay, answer A is coming. Okay, let's see one by one what are the with those answers are not there. The color of metal, will it matter? I don't think so, right? Because color doesn't deal with solubility, right? Shape of material, shape of material. Let's say you have one sugar like this and one small sugars like this. Okay, the rate of dissolution of this will be higher than this, but the solubility at the end will not depend on the shape of the material, right? So that is also not true. Shape of the material, size of the material particle, same thing. Let's see the answer then. Answer is correct. Yes, temperature and pressure. Yeah. When we increase the temperature, there is possibility that the more uh, solubility of a material can increase and material can be in the solution state. Okay, nice, very good. Let's move forward. Okay, so regarding sintering, which one of the following statement about sintering is correct? Sintering is the process where materials are heated to the temperature below their melting point to enhance the formation of solid bonds. Sintering leads to complete melting of material, resulting in homogeneous material. Sintering occurs only in a metallic material and not applicable for ceramics and polymers. During sintering, the material is heated to above melting point, causing it to become liquid. Okay, try to answer this. Sintering. Sintering, I will explain you. When we have two material A and B, and we want to make a joint between them, then we will heat them at a particular temperature. Because of that heating, the atomic diffusion may happen in that, and as I explained before that, the alloy may form here and we can get bond, good atomic bond. So try to see where it is fitting from this A, B, C and D. Anyone? Anyone? Anyone with the answer? Okay, B answer is coming. Let's see what is the answer. Sintering leads to complete melting of particles, resulting homogeneous material. Oh, maybe you are linking towards the previous question. No, no, no. That is just the increasing solubility. Sintering is different thing. So the answer not B. Its answer A is correct. Sintering is the process where metals are heated to the temperature below their melting point to enhance the formation of solid bonds. So, they like as I explained, A and B is two material. They are heated and because of below the melting point, and that's why because of the energy, they will exchange their atoms and form a bond that is called as bond formation due to sintering process. Okay. Okay, nice try, nice try. No problem, no problem. Good. So the next one is like, which one of the following is correct for Gibbs phase rule equation? You have option A, B, C, and D, where F is the degree of freedom, C is the number of component, P is the number of phases. Right? There is a rule. Yeah, just you have to remember this. Try to answer. Anyone? Anyone is guesswork is fine. Okay, let's see the answer and then we'll move forward to the next question. So answer B is correct, where F is equal to P minus C plus 2, or which can be written as F plus C is equal to P plus 2. Okay, that's, you can remember like this also, where F is a degree of freedom, C is number of components, P is number of phases. Okay, this will always be equal. That is the Gibbs rule. Like addition of degree of freedom plus number of component is always equal to number of phases plus 2. Okay. Okay. So yeah, we will study about the binary diagram now. So in the multi-component system, melting occur over the range of temperature. right? As you can see it here in a binary phase diagram, this is the composition of two different materials like polycrystal material from 0 to 100 and solid solution from 0 to 100 in reverse direction. Okay. So, this is the composition of weight on the x axis and temperature on the y axis. So, as the temperature changes, this composition varies, right? Initially everything is in a liquid state, you can see it here, everything is liquid. When the temperature is dropping at this location, the liquids convert into alpha plus L liquid. So, some amount of alpha is formed here, right, which is a binary phase now. And when the temperature further reduces, everything is becomes alpha, right, like this. Polycrystalline solid liquid solution, where crystalline of solid solution is also present together at this level of temperature and this level of composition, where at this location if you want to see, the polycrystalline material will be 40% and solid solution will be 60% at this location, right. Yeah. So, the melting occurs over the range of temperature between the solidus and liquidus line. This is liquidus line, this is solidus line. Okay. Liquidus line is line above which the material is converted totally into liquid, and the solidus line is below which material is converted into solid. Okay, this is solidus line. Okay. And liquidus lines, solids and liquid phases are in equilibrium in this temperature range. Okay, so they are in the equilibrium. So yeah, at this location you can find out what is the composition at particular temperature. It's also possible by using binary phase diagram. Hope you guys will study further into the online lectures and try to solve some of the questions from online assignments regarding binary phase diagrams. If you have any questions, you can reach me towards NPTEL discussion forum, where we are active to solve all the questions and queries regarding any doubts regarding the material course of MCM. Okay, and you can mail me to this mail IDs also, that is also possible. So, this was for today's lecture. If you have any questions, you can just unmute yourself and we can discuss. We have studied binary phase diagram, and then we have seen the Gibbs rules. Then we also studied what is the sintering process in the material, how the sintering process creates the bond. Then we have studied the solubility of material, how the solubility of material is dependent upon temperature and pressure. Then we have studied the phase diagram and how the pressure and temperature can control the state of any material. Then we also study, again the phase diagram again. And then we study the very good example of de-icing salt is possible for NaCl is possible or not. And then we also study about the atomic diffusion, how atomic diffusion happens. Here we explain about that is required a particular amount of activation energy to happen. Then we also study about dislocation movements, how the grain boundaries prevent the dislocation movements, and we also study the dislocation movements which where it is most favorable and where it is not favorable. Then also we study the difference between slip and twinning, and also we have studied about the slip in the general, and then also we have studied the how the movements of atoms in lattice and what are their interatomic forces and distance in general. Okay, so this was for today's live session. If you have any questions, you can reach me out through these mail IDs. Our NPTEL discussion forum is also live. I already have answered some of the questions. Remember that now the week 1 and week 2 recordings is live on YouTube. You can go and watch. Towards the channel name is this CE21D005. or maybe you can type this email ID also. You can get the channel and you can see week 1 and week 2 MCM live session, week 1 and to week 2. I will upload week 3 also soon. Today is not possible because of some issues. Tomorrow I will try to upload. Okay, any questions? You can unmute yourself, or any general question, no problem. From today's content you can ask from previous live session also if you have any questions. Okay, then thank you so much for joining today. We will see for the next live session, same timing next week on Monday. Thank you all.